These factories are incredibly expensive. They cost tens of billions of dollars, and they will not be generating any kind of return on investment for many, many years.
Inside the very device you are watching this video lies a series of semiconductors that run every program in existence. As our devices have gotten more powerful, smaller, and less energy consuming, it's forced chip fabricators to up their game. A lot. How much? A modern chip fab now costs billions of dollars for a single facility and can take years to construct and years to train a full operating staff. These facilities are the very opposite of startups, where you fail fast and seek a minimum viable product. In the past year, both TSMC and Micron have announced plans to spend $40 billion on new chip fabs in the United States, while Intel last month announced a $32 billion two-fab operation in Germany, and Samsung announced a $17 billion fab in Taylor, Texas. Why the sudden surge? Last year, the CHIPS and Science Act was passed by Congress and signed by President Biden, which incentivizes further expansion of chip fabs. Similar programs are being set up in the European Union and in South Korea. But that doesn't answer a key question. How did any factory in the world start to cost so much? And what must the US do to build these factories and compete going forward? Let's turn back to my Lux partner Shahin, whose life story is the recent story of chips in America.
So I did my PhD in electrical engineering, and the focus of my research was on microelectromechanical systems, or MEMS, and analog circuit design. So a lot of what I did in school was learning how to design microchips and to also come up with manufacturing processes that would build mechanical devices into semiconductors. So a lot of the early funding for semiconductors came from the Department of Defense through a lot of these defense primes. So you had a combination of academic talent being cultivated at places like Stanford and Berkeley. You had a lot of the executives moving out to the West Coast from the East Coast along with their engineers, building companies, and this demand from Department of Defense for a lot of the products that they were making.
The Department of Defense has traditionally been the most important institution guiding and coordinating the industrial policy of America's chip fabs. And it's a history that goes back decades to the Cold War and the Soviet Union, as Chris Miller, the author of the book Chip Wars, talked about recently on the Securities podcast.
Well, just as the U.S. was trying to guide its missiles more accurately, so too was the Soviet Union. And if you rewind the clock to the late 1950s, today we now know that the U.S. won the technology race with the USSR, won the arms race. But at the time, it was far from clear. 1957, right before the first integrated circuit was invented, the Soviets launched Sputnik into the Earth. They followed that shortly with Yuri Gagarin, the first person in space. And so at the time, it seemed like the Soviet Union was a really technological competitor to the United States. And it wasn't only in rocket technology, it was in nuclear weapons, where sure, they stole some of the technology from the US, but nevertheless, that was a real accomplishment. And at the time, it was possible to read any number of stories, for example, in the US press of the Soviets are about to overtake the United States in technology. And depending on what metrics you were looking at, you could find a lot of evidence for that. For example, numbers of engineers trained. The Soviets trained a ton of engineers and scientists. So there was real fear at the time that the Soviets were going to overtake the US. And they started pouring money and resources into microelectronics as well for the exact same reasons, a desire to miniaturize computing power and put it in weapon systems. And they invented their first integrated circuit just a couple of years after TI and then Fairchild did the same in the US. But they faced huge problems in actually building out their infrastructure for a number of reasons. One was that they never had a vibrant consumer market, whereas in the US, although chips started being almost exclusively sold to defense and space uses, by the 1970s, they were being sold widely to commercial uses for computers, for pocket calculators, things like that. In the Soviet Union, that was not the case. There wasn't a big consumer market, and so the overall amount of spending on chips was substantially lower because you didn't have those consumer use cases. But in addition to that, the Soviets didn't globalize. They globalized with Romania, they globalized with Hungary, the Eastern Bloc, but the US from basically day one was bringing in cheap labor from Southeast Asia, was bringing in vast markets in Western Europe and Japan, and had the industrial base of the entire industrialized world on its side. And so you could, if you were TI, turn to producers in Japan or Western Europe for equipment if you couldn't find it in the US. And that was something the Soviets could never do.
America had an indomitable lead coming out of the 1980s in chips and hardware, driven by market demand for personal computers that helped the industry use bountiful profits to flourish against Soviet competition. But slowly, and then suddenly, the industry began to outsource more and more of its hardware manufacturing over to East Asia, as Chris Miller just described. Today, the vast majority of chips are produced in South Korea and Taiwan, with critical materials from Japan and ultraviolet lithography equipment from the Netherlands. America finds itself out of the loop on chips. So what happens next? Here's Shahin testifying to Congress last month on this very subject.
Semiconductor development, which is the core of this technology, there is ultimately a trade-off between narrow functionality and or breadth of functionality and performance at a single use case. And so if there was a decision made to build resources that were targeted at training large language models, for example, I think it would be possible to quickly catch up and build that resource the same way we built specific resources during World War II for a certain type of warfare, and then again during the Persian Gulf War. So I think we as a nation are capable of doing that.
We want the fabs, but the fabs are really, really expensive. Why?
Now, what we've observed in semiconductors is that the cost of the machines and the tools that manufacture the semiconductors are incredibly expensive. So to make a car, you may need a press, you may need welders, you may need an acid bath. In the case of semiconductors, the components that you need to be able to produce a chip are orders of magnitude more expensive than what you would need to build practically anything else. And as a result of that, chip manufacturing has been highly centralized in countries and geographies where there has been meaningful government support.
This outsourcing trend didn't happen by accident, but was a deliberate program of economic coordination that these governments led to build themselves into the leading powerhouses of the chips industry. Investment funds for expensive fabs were coordinated by the government, which created linkages between factories, universities, and researchers to ensure that fabs had both the physical infrastructure and workers they needed to thrive. These programs took decades to come to fruition, but have generated immense profits today, as Chris notes next.
The Taiwanese have been trying to break into electronics since the 1960s. They looked at what was happening in Hong Kong in the early 1960s, which was the first place that US firms offshored their assembly and packaging. And they realized this was an industry that required lots of workers, required at the start relatively low skill levels, and could provide a substantial amount of employment for their populace. So the Taiwanese government was very focused on trying to attract US and also Japanese firms to build assembly facilities in Taiwan. And as a result of that, by the 1970s and 1980s, they had a substantial chunk of workers who had been in semiconductor facilities for some time. Taiwan also benefited because there were a lot of Chinese Americans and Taiwanese Americans, and of course the boundary between those two categories was complicated at the time, who were educated at Stanford or Berkeley or Purdue, who were very talented in electrical engineering, had worked at Fairchild or Texas Instruments, but also had some sort of connection to Taiwan. And so they were very skilled at taking advantage of those individuals, of whom there were many, to transfer information and expertise back and forth. And there's great examples of the Taiwanese government setting up all sorts of working groups and committees of Chinese Americans or Taiwanese Americans to advise on the development of their industry.
These were areas where there was a high level of emphasis and a high level of support that brought these manufacturing centers to those countries, which is the same thing that we're seeing with the CHIPS Act, with almost $50 billion being allocated to incentivize companies to build semiconductor manufacturing plants in the US. The CHIPS Act is simply a replica of what we've seen happen in other countries, which brought chip manufacturing to those countries decades ago.
America's investment into fabs with the CHIPS Act is a milestone. But it's a milestone that comes decades after other countries built similar programs. What matters next is how the US follows up that historic investment with further actions. Can we align our education policy in K-12, college, and graduate school to create a robust and diverse pipeline of chip engineers? Can we build the right physical infrastructure, from water utilities to roads, that ensure that these factories have what they need to succeed? And can we design our subsidies and credits and match them with overseas lending banks to create the export markets for our products? That's the next phase for bringing chips back to America, and the stakes only get higher from here.